Hello students, in this video we'll discuss the principal curvatures of a surface. Let's let S be a surface with first fundamental form given by E du squared plus 2F du dv plus G dv squared, which I'm going to denote as Roman numeral number 1. And second fundamental form two, which is L du squared plus 2M du dv plus N dv squared. And what we'll do is we'll form matrix versions of these forms, right? So we'll write 1 as the matrix E, F, F, G, and 2 as the matrix L, M, M, N. 1 and 2 are symmetric matrices, okay? We define the principal curvatures of S are the roots are the solutions of this equation, of solutions of determinant of 2 minus lambda times 1 is equal to 0. Okay? Excellent. And so, of course, what we're really doing here is we're asking the question, when is 2 proportional to 1, right? So what that really means is we're asking the question, when is 2 proportional to 1? And of course, remember that the second fundamental form was defined to be the differential of the first fundamental form as we moved along the normal translates of the surface, right? So in some sense, it's asking the question, when is that an exponential deformation of these things? Okay, excellent. Now we're going to do some modifications of this. And so what we can do is we can say, since that 1 is invertible, since 1 is positive definite, right? By assumption, that's what metrics have to be, and invertible, this is equivalent to, I can pull an I out of here, determinant of I inverse 2 minus lambda identity is equal to 0. In other words, these principal curvatures are eigenvalues of this matrix over here of I, -1, 2. Okay, excellent. Now, of course, we'd like to just say that these things are real numbers. We can't do that anymore because I know that if I have two symmetric the inverse of a symmetric matrix may no longer be symmetric, right? That's the downside of this. So we want to use some linear algebra to help us out with this though, right? And so what I can do is the following. So recall, given two vectors v1 and v2, we have that v1 dot v2 with respect to this metric. Well, this, of course, is the inner product with respect to the first fundamental form, is exactly going to be the vector v1 transpose, then this matrix 1, then the vector v2, like that. It's this quadratic form over here, right? And so now what I want to do is the following. So I want to choose two perpendicular vectors that are also unit, v1 hat and v2 hat, such that what? Such that, okay, not such that, but these things, if they're perpendicular unit vectors, what does that mean? That means if I form this matrix, v1 hat V2 hat transpose, hit with the first fundamental form matrix, hit with this matrix over here, V1 hat, V2 hat, then this will be just identity. Okay? And so let's set V capital just to be this matrix over here, V1 hat, V2 hat. Okay? And then what I'm going to do is I'm going to construct an auxiliary second fundamental form, construct and what will 2 tilde be? 2 tilde is going to be this matrix V transpose 2 V. And now note 2 tilde is symmetric. And that implies that there exists a W by the spectral theorem I can find a W orthogonal matrix, W transpose, such that W and then 2 tilde, and then W is going to be a diagonal matrix, lambda 1, 0, 0, lambda 2. I can unitarily diagonalize 2, right? So we're W tilde, W transpose W is just the identity matrix. It's the orthogonal diagonalization, right? Good. And so now what we want to do is the following. So now I want to consider, how should we do this? What do we have over here? We have this equation over here. So I want to consider the situation where I have dW. So if I look at W, construct, let's consider now I might get the message. Let me think for a second here. I want to do this to apply to I first. So where's my I? I's over here. So I need to have the V on the outside. So I want to consider VW. Let's call this matrix over here A. Then let's look at A transpose IA. Will that be? Well, this is going to be W transpose V transpose I, and then V, of course, VW, IVW. Now this, of course, is just the identity, so this is going to be W transpose W, and therefore that's just going to be the identity, right? So if I apply this matrix A to I, you get this. Now, what if you apply A to to 2, right? So remembering what what 2 was, right? So 2 is this thing over here. So if I apply A transpose to 2, to A transpose, what will this be? This is going to be the same thing over here. It's going to be W transpose V transpose 2 V, and then W transpose, just W. This thing over here is 2 tilde, so this is W transpose 2 tilde W, and that is lambda 1, 0, 0, lambda 2, like that. Excellent. So we're busting out a little bit of linear algebra to help us out here, which is really great. Shows us the power of linear algebra. And so now, determinant of let's just do it like this. We can do this top equation over here, actually. So let's look at the top equation. Determinant of 2 minus lambda I equals 0. If and only if I hit on both sides with A, right? If and only if determinant of A transpose 2 minus lambda I A equals 0, okay? By unitary similarity of eigenvalues. And now, of course, what is A transpose 2A? A transpose 2A is this diagonal matrix, and this is true if and only if the determinant of lambda 1, then a 0, then a 0, then a lambda 2, minus lambda identity is equal to 0, which is equivalent to saying that lambda is equal to lambda 1 and lambda, or lambda is equal to lambda 2. In particular, we know these lambda 1 and lambda 2 are real, right? So lambda 1 and lambda 2 are real here by the spectral theorem, right? And so that proves that the principal curvatures are real. The principal curvatures are real. And if these V1, V2, so if 2 V1 is equal to kappa 1 V1, and with an I, of course, I, and 2 lambda 2 is equal to kappa 2 I V2, then by hitting both sides with a V1 over here and a V2 over here, that will tell me that V1 hat is perpendicular to V2 hat over here. So in other words, not only that, but these principal directions, these directions of principal curvature are perpendicular to each other, right? So this is the eigenvalue, eigenvector equation for kappa 1. This is the eigenvalue for kappa 2. Again, if I hit this with what? If I hit both sides over here with if I put a V2 over here, V2 over here with that's going to be a V2 like that. Hit a V2 over here, V2, and put a V1 over here, put a V2 over here, a V1 over here, and a V1 over here. Well, what's that going to be? That's going to be the inner product of V1, V2, kappa 2. That's going to be the inner product of V2, V1 by symmetry, kappa 1, and those things are symmetric. So this expression over here and this expression over here by the symmetry is the same exact expression. So that says that kappa 1 V1.V2 is kappa 2 V1.V2. The only way that can happen is if V1 and V2 are perpendicular to each other. So I have a beautiful result that the principal curvatures of a surface are not only real numbers, but the directions of principal curvatures have to be perpendicular to each other. In further videos, we'll examine what further properties we can glean about the surface from these two principal curvatures at any point. Thank you very much.